morning, ladies and gentlemen. I'm going to present this work. This work is basically was developed by a PhD student. We don't see it.
No, maybe it's switch off.
No, it's very bright.
Ah,
very bright. So Fernandes is finishing his PhD, so this is part of his work. He's done the most of the experimental part, and it was developed by Professor Jesus, by myself, and Professor Branco and Costa from Coimbra University. So the outline of this presentation is a typical one: introduction, motivation and goals, some experimental procedure, the results, and conclusions. So as you know, additive manufacturing is somewhat indicated for some complex shapes, permits some temperature optimization, and also some weight and waste reduction. Typically, the laser power bed fusion technique is applied to the alloys, aluminium, silicon, tin, magnesium alloy. Of course, we, as all manufactured pieces, we have some defects causing electron fusion, and in this case, we also have important, as we will see, residual stresses. Another thing for this alloy is that it's very important. The heat treatments have a huge impact in this kind of alloy because there's a transformation for high temperatures. We have precipitation of the silicon and we lose a lot of mechanical properties of the alloy. So we have to have that in attendance. So the objective of this, the motivation is the optimization of the heat treatment. So we will do temperatures below 260 degrees to maintain the aluminum silicium network as stable as possible, and for that we will try to have a ductility, synergy, strength increase, and the stress relief with those treatments. So we will go to get the crack growth rates, to see some failure mechanisms, and to analyze some crack paths in the cell. The specimen is a typical one. It's a CT specimen accordingly to AlSi10Mg 647. The machine is an initial machine. The specimens were performed there with a laser power of 350, 30 microns of layer thickness, and with this laser, the scan speed. 2 heat treatments were performed. The stress relief one, so we don't pass the 260 low temperature, 250 for 2 hours, followed by water quenching, and then a heat process with the same temperature for 2 hours and with operation of 100 megapascal. The tests are performed in an Instron electron pulse machine with 10 kilonewtons. You can see here a figure. We have 2 systems to acquire the data. We have a traveling microscope to measure the crack growth rate, and we have a DIC system to measure crack closure. And the parameter, the U parameter, the load ratio parameter is defined as by this equation, P maximum minus P open, so the delta P. So some results, here we can see microstructures of the S-build series. We have point 1, the zone 1 is the inside the melt pool. We have a fine cellular microstructure. Then we have the boundary here. We have a coarse microstructure, but here is also very coarse when the melts or against one another. And finally, we have in point 4 a dendritic columnar structure in the solidification direction. So here we can say that the specimens are mainly composed by a supersaturated aluminum silicon cellular dendritic network. This figure presents the monotonic behavior for the 3 conditions. So I will present always 3 conditions: the S-built, the stress relief series, and the heat series. So basically all the same with 2 heat treatments. So we can see that there is a loop. We lose both the yield strength and the final strength, 10%, 30%, and 16% in the yield strength, but we can increase the ductility of our alloy, and this increase is small because if I perform, for example, I have performed it a T6 typical for aluminum alloys, we will get a decrease of 50%. We can't use that. This figure presents the crack growth rates. We have done two tests for each condition. We have the full symbols of for K increasing procedure and the open symbols for kappa decreasing to get the threshold value. Thank you. So here in this figure, we can see the values that were obtained for the Paris constants, and here we can see the values of the threshold around 1. Which is typical for aluminum alloys. For aluminum alloys not made by SLM, the typical value is 1.1. So it's more or less the same. And we can see that the stress relief, and this is the AB series, the blue one. So the other treatments, we have a decrease in crack growth rate, so an increase in the behavior against crack growth. So we have similar, but for the two treatments, we have similar curves. Here we can see the crack closure, the load ratio parameter against delta K, and there are two regimes. This is regime 2 of crack propagation and the threshold regime. Of course, here we have an influence of crack closure because we have low loads, but in the regime 2, we don't have crack closure because we have a level of 1. So we can say that in that case, the crack is opening from the minimum load. We don't have crack closure. In regime 1, has lower values, of course, and showing existence of crack closure, and this also explains the crack deflection of the J.D.M curves. What is the cause of this? We think that is due to roughness effect. That is more important, of course, in the threshold zone. There's a contact between the crack faces, and we can see here the difference of the asperities in regime 1 and in regime 2. And in regime 1, we have high peaks and higher values of the roughness, and this can explain the existence of crack closure in the zone, but plasticity-induced closure, we couldn't see it. But we will activate it with overloads, as we'll see later. This is the residual stress profile along the thickness of the specimen. We can see here that for the not heat-treated specimens, we have an increase in depth, in intention. So residual stresses in tension are not good for fatigue, as you know, and the treatments, the above heat treatments could reduce this stress, this residual stress, and maintain it more or less constant around only 50 megapascal. Then we perform some overloads to see if we can activate the plasticity induced closure mechanism. Here we have two curves, the blue ones for the as-built material and the red ones for the stress relief heat treatment. We have a general behavior for overloads. We have a decrease in the load, in the crack growth rate, then we have an increase again, and then we get the value that we would have if there was no overload. And in the other figure, we see the U level parameter, and as you can see now, we have a decrease in this, important decrease in this parameter. What means that we have activated the crack closure, the plasticity-induced crack closure. So the behavior is similar, and the crack closure can explain the behavior of the curves. This conference is about crack paths, so we have to show something about crack paths. Here we can see the lateral macrographs of the three specimens. The A is for AB specimens, base material. B is for stress relief, and C is for hip specimens. They basically are the same. We have crack propagation is predominantly interlayer, with some interlayer failure near only the boundaries. And the propagation modes are similar for the all three modes. Here we can see also the fracture surfaces after applying some overloads. We can say that we observe the same for the free materials, and we can observe a lot of micropores and defects. Here it's visible, and this is the mark of the overload, of course. Here there is a comparison between two specimens, the base material and the stress relief specimens, and there are some differences. The marks are visible for the lower figure. It's for the base material, and the failure occurs just after the third overload. While in the stress relief specimens, only the mark of the third overload is visible. The others are not. It's more resistance to that, and the heat treatments promote an increase in the ductility and the toughness of the specimens. So basically, we can say that if this material is important for crack growth rate resistance, the stress relief treatment is important to perform, because we have an increase in this kind of resistance to crack growth rate. So I think I'm in time. The applied heat treatments induce slight microstructural transformations, resulting in a coarse aluminium silicon supersaturated matrix. The microstructural transformation result in a reduction of the strength but increase the ductility. The heat treatments result in a decrease of the residual stresses, and it was the main mechanism responsible for improving the fatigue crack growth. The higher ductility of heat treatment series did not influence the crack closure, and the load ratio parameter is similar to 1 for all test conditions. Fatigue crack propagation is predominantly interlayer with some interlayer failure near boundaries, and propagation modes are quite similar for the free materials. So finally, heat treatments enhance the ductility and the fracture toughness, giving greater visibility to overload marks, promoting a longer crack propagation period and a longer crack at the final failure. If you permit me, just telling you that as most of you, we are organizing a special issue of MPDE, of metals, and if you are interested in this, send me an email. I can waive you offering the publication of an article. It can be eventually interesting. Thank you very much for your attention.